Okay, so good morning, everyone. So today we are here for the defense of the Ph.D. of Belouadah, named Large-Scale Deep Class Incremental Learning, with a jury composed Niku Sebe, professor at University of Toronto, David Filia, professor at ENSTA Paris, Tine Tutelas, professor at Catholic Universitat, Simeon Papadopoulos, senior researchers at ET, Adrian Popescu and Ioannis Canelos, who are your supervisor, and myself, Céline Hublot, professor at Central Supélec. So you have 44 minutes to present us your thesis work.
Thank you. Hello, everyone. My name is Belouadah, and today I will be presenting my PhD thesis entitled Large-Scale Deep Class Incremental Learning. This thesis was done in CA List and IMT Atlantic under the supervision of Adrian Popescu and Ioannis Canelos. I would like to thank the jury for accepting to evaluate this work and the public who is attending the defense. In general terms, continual learning consists in learning from streams where data continuously appear upon the time, and the goal is to update our continual learning system using these data and possibly a subset of data from the past. The system is then evaluated on all data seen so far. Each cycle in continual learning is called a state, experience, or task, depending on the application domain. In this thesis, we will call it a state. Incremental learning is interesting in dynamic environments where resources in memory and computational resources and execution time are limited. As application examples, we can find a face recognition system where the different identities appear at a fast pace continuously. We can find robots that explore autonomously the external world in a continuous manner, and we can find health applications where access to past data is impossible due to privacy constraints. There are three scenarios in continual learning. The first one is called task incremental learning. Here, the new data appears in groups of classes that we call tasks with known task boundaries. It means we know how many classes there are in each task. Also, during testing, there is an oracle that provides an information about to which task belongs the testing image to guide the inference process. This is the easiest scenario between the three. The second scenario is called class incremental learning. Here, the new data also appears in groups of classes with known task boundaries. However, there is no information during testing regarding the task ID of the test image. The third scenario is called domain incremental learning. Here, data does not necessarily appear in groups of classes. There are no task boundaries, and it means also that there is no information regarding the task ID during inference time. In this thesis, we are interested in class incremental learning applied on image classification using convolutional neural networks. The main problem of continual learning algorithms is catastrophic forgetting, is the tendency of neural networks to underfit past data when trying to learn a new one. Practically, this means that if we update the model using a new data only in each time, this leads to a bias of the network in favor of new classes. And we can see this in the figure on the right in terms of the classification scores of past and new classes that we plot here in each incremental state from 1 to 9. We notice that the gap is large between the two types of scores. And also this means that when we provide a testing image to the network, it will probably be predicted as belonging to a new class, even if this is not necessarily the case. Here are some notations that I will use in all the slides. A is continual learning algorithm. T is the total number of states. S is a state. P is the number of new classes in this state. N is total number of classes seen until this state. K is a memory to store images. I is a secondary memory. M is a model. F is a feature extractor. C is the classification layer. W is the weights matrix in the last fully connected layer. And O is the output scores vector. There are two scenarios in incremental learning. We have incremental learning with memory, and we have incremental learning without memory. Here I present one toy example with one initial state and two incremental states. In each state, we have two new classes that appear and should be included in our system. In the initial state, we perform training from scratch using data of the two first classes. And in the two incremental states, we update our model using an incremental learning algorithm A, using all data of new classes and a bounded memory K of data from the past. Note that the more we add incremental states, the more is the imbalance in favor of new classes, because past classes have less and less representatives for them in the bounded memory K. In incremental learning without memory, the process is the same. However, the difference is that each time we update the model using data from new classes only. So this is a most difficult scenario and more useful in practice. The bias of the network towards new classes increases as we reduce the number of images in the memory. So here in this figure, we can see in the left, we have 20,000 images in the past, and we reduce it until 5,000 images of the past. And we can see that the gap in scores between new and past classes increases. In the rest of the presentation, I will first present the most important works in the state of the art, as well as their merits and limitations. Later, I will pass to explain our contributions with memory of the past that we named Diesel, IL2M, Scale, and FTTH. And because we are also interested in real life applications, we propose two contributions without memory of the past that we call SAW and the Transseal. Once I present all our contributions, I will pass to present the experiments and discuss the main results. And I will finish with some conclusions and the future work. There are three main categories in continual learning. The first one are methods that are based on fixed representation. And these methods, they train the model on the first batch of classes and they freeze it afterwards. The second type of approaches is based on fine-tuning, and this is the most popular kind of approaches. And here we have three subcategories. The first one are methods that use a memory of the past to refresh the model. The second type are methods that do not use memory of the past. And the third subcategory are methods that generate images of the past instead of storing them. Replay and no replay based methods either use bias removal layers or regularization to tackle catastrophic forgetting. The last type of approaches are parameter isolation based. And here we can find fixed networks that compress the neural network, or dynamic networks that expands its architecture in order to accommodate new classes. Please note that in this schema, our contributions are in green. We identified 6 properties that qualify an algorithm to be class incremental. The first 3 of them are inherited from Ribalfi and his colleagues. So first, the complexity of the model should stay stable or nearly so, as only the classification layer should evolve in order to be able to classify new classes. Second, the model should be able to work without memory of the past or with a bounded memory of the past. Third, the model should be performant not only on new classes, but also on past classes. Fourth, the delay needed to accommodate the new knowledge should be bounded. Fifth, the model should do the best compromise between plasticity of the neural network to adapt to the new data distribution and its stability to keep as much as knowledge from the past. And finally, the model should be able to learn an unlimited number of classes. Unfortunately, none of the methods from the state of the art satisfy the 6 properties in the same time. So in general, there is a compromise that is done depending on the application domain. Fine-tuning based methods, they have complexity that increases slowly. and they achieve the best state-of-the-art results with the memory of the past. However, a retraining is needed at each incremental state to accommodate the new classes. The fixed representation-based method also have a complexity that increases slowly. They are not dependent on the memory of the past, and they include the new classes fast because no retraining is done at each incremental state. However, their quality is heavily dependent on the quality of the fixed representation. For the parameter isolation-based methods, they do not depend on the memory of the past, and they have a good compromise between plasticity and stability. However, a retraining is also needed at each incremental state. The root method of most class incremental learning method is called learning without forgetting, is based on fine-tuning, and it adapts knowledge distillation to class incremental learning. Knowledge distillation encourages the neural network to reproduce the same output for past classes as in the previous state. It thus requires saving both the current and the previous model. The advantage of this method is that it does not use memory of the past. However, the gap with a joint training in which all the data is available at once is still large. The second method is called ICAR, and it's an adaptation of learning without forgetting to the case of incremental learning with memory. The authors propose a herding mechanism that helps us to select the best exemplars to fit in the memory. So mainly the exemplars selected are the subset of images that best approximate the real mean of the class. And finally, they propose a nearest exemplars mean classifier that is an adaptation of nearest class mean classifier. And here the predicted class is the class that has the nearest mean to the image that we want to classify in terms of a feature vector. So ICAR combines powerful components. However, it's based on an unfair comparison with baselines, as ICAR was tested with a memory of the past, and all the baselines were not allowed to have a memory of the past. And this leads to wrong results regarding the fact that distillation is more powerful than a vanilla fine-tuning at large scale when we have memory of the past. The third method is called LUCIR, and it combines three main components. The first one is cosine normalization to balance the magnitudes between past and new classes. The second is less forget constraint, and it's an adaptation of distillation to work on future vectors instead of classification scores. And the third is interclass separation to better separate the past and new classes. So LUCIR combines a powerful objective. However, it requires important execution time compared to the other methods from the state of the art. The last method that is interesting is called bias correction. And this method is based on distillation loss, followed by a bias removal layer. This bias removal layer contains two parameters, alpha and beta, that we use to reduce the classification scores of new classes and give more chance to the past classes to be selected during inference. This method is thus simple, fast, and performant. However, it has two main drawbacks. First, it requires validation sets to estimate the calibration parameters. It means it is dependent on a memory of the past. And the other drawback is that it treats all the past classes the same, and it assumes that the forgetting happens in the same way in all the past classes, and this is not necessarily the case. Now I will pass to present our contributions with memory of the past. The first method is called DSL, or Deep Shallow Incremental Learning. This method is based on fixed representation and is inspired by transfer learning. It has two main steps. In the first step, we train the fixed representation on the first batch of classes. And once the model is trained, we use the fixed representation in all the subsequent states. So here in the second step, I have my fixed representation that we will use to extract the features of all the future classes. And we train one SVM per class. to learn the classes incrementally. So the SVMs, they need positives and negatives to be trained. The positives of each SVM are the feature vectors of the associated class, and the negatives of the SVM are selected with a negative selector component that we developed. The advantage of Diesel is that it works with and without memory of the past. The second method is called IL2M, or incremental learning with dual memory. It's also, it is based on fine-tuning, and it's followed by a bias correction layer. So it shares the same spirit than the big method from the state of the art. However, it differs in the way we rectify the scores of past classes. So in IL2M, we perform in the first step vanilla fine-tuning, in which we save statistics about the classes when we learn them for the first time. And these statistics are saved in secondary memory I of negligible storage, and we use them later to rectify the scores of past classes in the subsequent states. So what are these statistics? Once we learn a class with all its data, we save the mean prediction score on images of this class, and also the confidence of the model in the state. The confidence on the model, we compute it as the mean top one prediction score averaged over all the training data of the new classes in the state. Now, how we perform the score rectification at inference time, we simply take the score of each past class and we multiply it by its mean prediction score in the initial state in which it was done for the first time, and we divide it by its mean prediction score in the current state. So this term helps us increase the score of past classes and make them more comparable to those of new classes. And the second term, we use it to harmonize the predictions that we are combining from different states. So we multiply by the confidence of the model in the current state, and we divide it by the confidence of the model in the initial state of the class. Here we can see the effect of IL2M on the prediction scores. So on the right, we can see that the predictions of past classes are more balanced, and the gap is less compared to those of new classes. However, this gap is still large, and more effort was needed to improve the results. The second method is called scale, or classifier weights scaling for class incremental learning. This method is also fine-tuning based, and in this method, we tackle catastrophic forgetting in the weights matrix instead of the classification scores. So here, in addition to the bias of the network in terms of classification scores, we notice in the figure on the right that the mean weights activations of new classes are also higher than those of past classes. For this reason, the idea of scale is to tackle catastrophic forgetting in one step before IL2M. In scale, we also perform vanilla fine-tuning in the training part, and in the inference time, we bring the classification weights of past classes from their initial states to rectify their weights matrix in the current state. And why we do this is because when a class is first learned with all its data, we hypothesize that its weights activations are higher. So we just override its weights in the current state. And later, since we combine weights that come from different states, we perform a normalization of the weights matrix. To do the normalization, we take for each state the class weights of the new classes. We sort them based on the absolute value, and later we compute the mean of all of these weights vectors dimension by dimension. And in this case, we have one mean vector per state that we will use for the rectification. Now, how we normalize past class weights, we multiply each dimension of the past class weight by its corresponding dimension in the mean weights in the current state. and we divide by the corresponding dimension in the mean weight in the initial states of the class. In the bottom, we can see the effects of scale on the classification scores. So we can see here on the right that the classification scores between new and past classes are more comparable, with a little overestimation in the earlier states of the class of the scores of the past classes. And the gap increases slowly as the incremental states advance. The last contribution with memory is called fine-tuning with threshold calibration. It's inspired by imbalanced learning approach, and in this method, we rectify the scores of all classes by multiplying the score of each class by the total number of images in the state, and we divide it by the number of images in the class. So this formula helps increasing the scores of all underrepresented classes. In this case, they are the past classes. So note that this method works with a memory of the past because we need also to estimate the number of images for the past classes. Now that I finished to explain our contributions with memory, I will pass to our contributions without memory of the past. The first method is called SIW, or standardization of initial weights for class incremental learning. This method is also fine-tuning based. And here, once again, we can see the mean magnitudes of past and new classes. So in blue, we have the new classes, and we notice the big gap in the mean weights magnitudes between the two types of classes. Also, we notice a variation between different states in the mean magnitudes of new classes. So the idea of SIW is to adapt our method scale to a memoryless setting. So the first step in SIW is the same one than in scale. We just replay the class weights of past classes from their initial state to rectify their weights in the current state. So this is the same step. What differs compared to scale is how we make the normalization of the weights matrix. We did a study on the weights that are in the last classification layer, and we found that they follow a normal distribution, as we can see in these figures. So we simply propose to standardize all the weights matrix for past and new classes, and we follow it by state mean calibration. And this is the same calibration that we used in our method IL2M. Here we can see the effect of SIW on the weights magnitudes. We can see in the figure on the right that the weights magnitudes of past and new classes are more comparable, and also the weights magnitudes of new classes across the states are more stable. The last method is called TransIL, or dataset knowledge transfer for class incremental learning. This method is also fine-tuning based, and the idea is to apply this method on top of other class incremental learning methods to increase their performance. In these two figures, we see the scores of learning without forgetting and Lucir. And we notice that in both of the cases, even after applying the two methods, there is a bias of the network towards the classes that are learned in the later states. So the goal of TransIL is to reduce this bias. We use as baseline the bias correction layer that I already explained in the state of the art. As I already said, the drawback of this method is that it only reduces the scores of new classes, and it assumes that that the forgetting happens equally in the previous states. So we propose to modify this method, and we propose adaptive bias correction layer. In this layer, we use one pair of alpha beta to rectify the scores of all the classes in all the states. And here we can see that we have a better distributed scores over all the states. Now, both BEAC and adaptive BEAC, they need a validation memory to estimate the calibration parameters. So how we can deploy them in a memoryless setting. The idea is to transfer the calibration parameters between one reference dataset and one target dataset. In the top figure, we can see the training on one reference dataset that we learn in an offline manner. It means that we assume that for this dataset, we have validation memory here. So we use the validation memory to estimate the calibration parameters of adaptive beak on this dataset. Now, once the training is done, we only save the calibration parameters in a secondary memory I of negligible cost. And we use these saved parameters to rectify the scores on the target dataset. And here, in the case we have more than one reference dataset, we simply compute the mean over all the calibration parameters before to transfer them on to the target dataset. And here we hypothesize that the calibration parameters are stable enough to be able to transfer them from one dataset to another. We optimize the calibration parameters on the validation set of the reference dataset using a simple cross-entropy loss. On the right, we can say an average calibration parameter values, and we can see that the more the class is far in the past, the stronger is its calibration parameter, and this is intuitive insofar as the past classes in earlier states are those who suffer more from catastrophic forgetting. It's also interesting to notice that the variance in the calibration values on top of Lucir are more stable compared to those on top of learning without forgetting. Here we can see the effect of our methods on the classification scores on learning without forgetting and Lucir, and we can see that for both methods, the scores are more balanced, and the scores of the earlier of the classes in the earlier states, they are less because they suffer more from catastrophic forgetting. In terms of correct and wrong prediction, we can see that after applying our method, the distribution of correct predictions is better distributed over all the confusion matrix. Now, after that I explained our contribution with and without memory of the past, I will present the experiments and discuss the main results. We evaluated diesel IL2M scale FTTH and SIW on 4 data sets, where the first 3 data sets contain 1000 class and the last data set contains 100 class. So ILS, VRC, and CFAR are designed for object detection. VGG phase 2 is for face recognition. Landmarks is for tourist landmark recognition. We use in all our experiments a ResNet 18 architecture, and we vary the memory size between 2, 1, 0.5% of the training set and no memory at all. We vary the number of states between 10, 20, and 50. And note that K and T are the most important 2 parameters to vary to test the robustness of class-incremental learning methods. To evaluate Transil, we use 10 reference data sets that we make from ImageNet leaves, and we use 4 target data sets that are CFAR 100, ImageNet 100, that is a subset of ImageNet that is different from the reference datasets, Birds 100, that is also part from ImageNet, but it contains fine-grained classes of birds, and Food 100 for food recognition, and it has large domain shift compared to ImageNet. We also use ResNet 18 architecture in all the experiments without memory of the past, and we vary the number of states between 5, 10, and 20. We compare our methods to vanilla fine-tuning, end-to-end fixed representation, iCarl, Lucir, Beak, Remind, that is a fixed representation based method, and without memory we compare with fine-tuning, fixed representation, learning without forgetting, that is a version of iCarl without memory. We also compare with Lucir, Remind, as well as FT plus, that is equivalent of SIW without standardization, and deep SLDA, that is also a fixed representation based. We apply some simple plugins on top of fine tuning to test the robustness of this method against the distillation loss. We have init. It's when we use the initial classifier weights of past classes in the same way we did in scale and SIW. L2 is when we use to normalization of the weights matrix. MC is the mean state calibration that we used in IL2M and SIW. TH is the threshold calibration layer from our FTTH method. BAL is when we reduce, it's an extra step after fine tuning in which we reduce the number of images for new classes and to have the same number of images in the past for the past classes. NAM is the nearest exemplars mean from ICAR. We also compare with the upper bound method in which all the data of all the classes is trained, is available at once. To evaluate the different methods, we use the average incremental accuracy. We don't include the accuracy on the first states because it's not incremental. We also propose a GL aggregation measure that provides one single value aggregated over all the tested configuration, and it helps us to compare the different methods in simple way. Note that this measure gives negative values, and the closer the value to 0, the better is the method. Here in this first slide of results with memory using the herding procedure from ICAR, I fix the number of states to 10, and I vary the memory size between 2, 1, and 0.5%. Results show that when we compare ICAR, that is distillation-based method, with vanilla fine-tuning, we notice that fine-tuning outperforms ICAR in many cases, especially when we have enough exemplars in the memory. And this is surprising compared to the results initially reported in the ICAR paper. So we decided to remove distillation and replace it with simple plugins that I already presented. And surprisingly, all these simple baselines outperform ICAR with a subsequent margin. And this helps us to deduce that distillation is actually not needed when a memory of the past is available, especially at large scale. And this also can be explained by the fact that distillation leads to confusions between past classes the more we have classes in our dataset. Lucir and Big, they have more sophisticated components than the initially proposed distillation, and thus they have overall the best results of state-of-the-art in this configuration. Note that Scale and IL2M were published in the same time than Lucir and Big, and they are not far behind in performance in this configuration. The fixed representation based methods, they perform worse in this configuration because the memory helps compensating the catastrophic forgetting compared to when we freeze the network across the states. Finally, the gap with adjoint training is large, and it means that more effort should be done in class incremental learning in order to improve the results. In this second slide of results, I fixed the size of the memory to 0.5%. That is the most difficult case because the bias in favor of new classes is higher, and I vary the number of states between 20 and 50. Note that in this slide on the right, I present the global measure GEL. Results show that the best overall results are obtained with our FTTH method in terms of individual scores and also in terms of the GEL score. And this method is followed closely by Scale. So it's the second best method in this configuration. Note that our methods outperform Lucir and Big with subsequent margin in this configuration. And this means that our methods are more robust against the variation of of the number of states. Finally, the fixed representation-based methods suffer more in this configuration because the fixed representation is learned with less classes in the initial state. Without memory, when we compare vanilla fine-tuning with learning without forgetting that has distillation, we found that learning without forgetting achieves really high results. And this means that distillation is useful when no memory of the past is allowed. When we replace distillation with initial plugins that we apply on top of fine-tuning, we improve the results of fine-tuning and also those of learning without forgetting on large scale datasets. However, learning without forgetting is still better on the small scale dataset CFAR. When we apply SIW on top of fine-tuning, we obtain the best state-of-the-art results on fine-tuning based methods for large-scale datasets. And when we apply SIW on top of learning without forgetting, we get the best results of fine-tuning based methods on the small-scale dataset CFAR. Overall, the best results in this configuration are obtained with fixed representations that are more robust against forgetting when no memory of the past is allowed. And diesel is the best method in terms of GEL measure in this configuration. In this table, we evaluate transil. So the first line for each backbone method presents its performance, its raw performance without any bias removal. The second line is when we apply on top of the method bias correction layer with a knowledge transfer. The third line is when we apply adaptive bias correction, our proposed method, plus the transfer of calibration parameters. And the last line is when we have an oracle that selects the best reference dataset from which we transfer the knowledge. The losses in the gains in performance are in green and the losses are in red. The results show that that both beak and adaptive beak, they obtain good results on top of the backbone methods, with adaptive beak being the best method in all the configurations. And also the gap with an oracle selection is small. However, it would be interesting to investigate more the effect of choosing other methods to select the reference dataset from which we transfer the knowledge. The best results are obtained when we apply adaptive beak on top of Lucir, and we have up to 14 points top one gain in accuracy on BIRD's dataset with t equal 10 states. Finally, the gap with joint is still large also in these experiments, and this means that class incremental learning is far from being solved. To conclude, the classification layer in fine-tuning is the most affected by catastrophic forgetting, as we saw in our experiments, because consequent gains in performance could be obtained only by tackling catastrophic forgetting in this layer. When a memory is allowed of the past, the best methods that achieve the results of the state-of-the-art are fine-tuning based. However, when no memory of the past is allowed, the fixed representations are a better choice. We found that the usefulness of distillation is reduced at large scale when a memory of the past is allowed. And it's also important to note that all our methods don't use distillation, and thus we reduce the model's footprint by half, because we only save the model in the current state and we don't use the model from the previous state. And our secondary memory that we use in most of our methods is of a negligible cost compared to what a model, what is the size of a model. In the future work, it would be interesting to investigate more the effectiveness of distillation compared to the size and the type of the datasets, and probably propose an alternative of it to tackle catastrophic forgetting. The second point is that it will be better to focus on class incremental learning without memory, because it is true that it's more difficult to tackle, but it is the most useful in real life applications. Also, more methods that better tackle catastrophic forgetting by doing the best compromise between stability and plasticity of the network are needed. And instead of just focusing on the classification layer, it would be interesting to tackle catastrophic forgetting in the earlier layers of the neural network. This is the list of the papers associated with this PhD. Note that 2 papers were not presented in this defense because the focus is put on the most important contributions only. All the codes and dataset details are in this GitHub repository. Thank you for your attention.
Thanks, Eden. So I propose to begin by the reviewer of your PhD. So I propose to begin by Niku Sebe, professor at University of Trento, Italy. Niku?
Okay, yes. Thank you, Eden. I think it's, well, you did quite a lot of work. I think it's what I really appreciate is that, and this was also reflected by the presentation, not only by your thesis, the fact that you are very careful in running experiments, putting details, and I think this is quite important. Because of this, your thesis is really a very good reference for, let's say, the state of the art, for the thing that you've been working. So I think it's quite useful for a few other people. So I really congratulate you for this work and the way you presented it.
Thank you.
Since I'm the first one, let me start with a little bit of, let's say, maybe intriguing questions a bit. I mean, just a little bit general. So I noticed also during your presentation that you are interchanging the 2 notions of incremental and continual learning. Are these synonym according to you, or is there any difference?
In general, we use incremental learning or continual learning depending on the community that tackles the problem. So the term depends from one community to another. So there is continual learning, incremental learning, and lifelong learning. And all of them, they share the parts of tackling catastrophic forgetting as the main issue, and the ability to adapt the artificial agents to new data that comes in stream. And now there are some differences that I highlighted in the 3 scenarios of continual learning, that are the task incremental learning, class incremental learning, and domain incremental learning. So these are the little few differences between the different terms used, but the goal is the same, is to don't forget what we learned in the past, and we adapt the neural network to new data.
Okay, I agree. What about online learning?
Online learning for me is when the data is the last scenario, that is domain incremental learning, in which the data comes sequentially, and normally each sample is allowed to be seen once by the neural network. So once the image arrives, it is injected in the neural network, and we don't have the right to perform epochs. So there is no notion of offline learning, that we perform 100 epoch or until the model trains. So each data arrives, it's seen once by our model, and that's it.
And are your approaches also able to deal with online learning?
No, because we use the statistics that we compute in general on the mean on the batch. So we need the task boundaries for this. So we need to know how many classes we have in each incremental state to be able to compute these statistics and to perform our calibrations. So we assume in our case that the data arrives in batches of classes.
So you could theoretically, but you can still kind of make it if you would do some sort of a buffer somehow. So you put some sort of a buffer, you put some online stuff into the buffer, and then you can apply your approaches.
Yes, of course. But in this case, as you said, you will keep a buffer. So it depends on which resources we allow ourselves to have. We can adapt the different methods.
Okay, very well. Another thing that I notice is that you always, and this is not a limitation, I'm just trying to understand exactly what you try to do. You talk always about new classes, but I was wondering, what about trying to do some sort of, deal with change into a particular class? So you are kind of doing some sort of adaptive learning. So can you still do it in this case? So in the sense that you are doing incremental learning, but on a particular class. So the class is changing once you are getting more samples.
I didn't get the question very well. Do you mean that if the past classes arrive, like again?
Mm-hmm.
Yes, yes, our methods still work, and they will be better because we are refreshing their representation. So in our specific experiments, we don't repeat the past classes, but the more they come back in the future, the more it means it's better for our system, because we assume that if a class arrives in the subsequent states, I mean, for the first time, it will have all its data. So we don't count in the memory the images of the new classes. So if one past class arrives again, so it will be good. So it's like we have a memory for the model.
Even if the past class is kind of changing a bit, because you may, let's say at the beginning, you may start with a few samples, so you get some sort of estimation of your mean and variance. But then once you get more samples, this will shift according to what you have.
Yes,
so
exactly, it depends on the way how our data set it is.
Mm-hmm.
For example, in these experiments, what we do is shuffling of all the images and all the classes, and after divide it. So we assume that the data is IID. Now it depends on if the distribution of this old class that appear for the second time is the same than the distribution. Mm-hmm. When we learn it in the past, I think there won't be a problem. Now, if it's the same class, but the distribution is different, I guess that it will be tackled in the same way as it is a new class. Because anyway, in the case, if we don't have memory of the past, we will probably lose the information about the past distribution of this class, and we will just adapt to its new distribution.
No, I don't mean that the samples are coming from a different distribution. I'm just saying that at the beginning, you may have only a very rough estimate of the distribution. So once you get more samples, then your distribution is getting better. And the estimation of the distribution, because at the beginning, if you have very few samples for a class, your estimation of the distribution is very, very rough.
Yes.
So that would be, okay, very good. So that I think that covers, let's say, the context that I wanted to hear. One thing that I'm curious about, and you discussed a little bit, but can you talk a little bit about, let's say, the limitation of your approaches? And for example, how are you dealing with outliers?
The limitations of our approaches.
Mm-hmm.
Okay, so I will start one by one. For diesel, that is fixed representation. The limitation of this approach, it depends on the fixed representation. So in the case the fixed representation is learned on small number of classes, or we have a big number of classes but with few images, so the representation is not strong. Mm-hmm. When I try to transfer the knowledge to other classes, the quality of these SVMs will depend heavily on the quality of this fixed representation, and especially if the domain shift is large between the incremental states and the initial state. So here, if I train on cars and houses, and after I try to learn my SVMs on birds, for example, it won't work. Yeah. So it assumes that the new data that appears has the same, more or less the same distribution. So this is the limitation of all fixed representation based methods, not only diesel. Now for IL2M, one of the limitations is that it requires a memory of the past to be able to function, because in this formula, we use the mean of the class in the current state. So it means we have exemplars of the class that we have in the memory, and we compute on them the mean prediction scores. So if we don't have memory of the past, we simply can't apply IL2M. And for scale, it's the same. Theoretically, we can apply it without memory, but in experiments, when we tried to do it without memory, the quality of the weights vectors in the current state was not good enough to be able to work with this normalization that we propose in this equation. So both IL2M and scale, they are dependent on the memory of the past. And even if we suppose that we have the memory of the past, if we have lots of incremental states, so each time we reduce the number of images in the memory for past classes, if the number of past classes exceeds the size of the memory, it means we have more past classes than number of images that we keep in the memory. There are some past classes that they won't have any more representatives for them in the memory. And this is a drawback of all methods that depend on memory of the past, not specifically IL2M and scale. Now, this method is also does not work at all without memory of the past, because here we need to estimate the number. We need to compute the number of images for past classes in the current state. So without memory, this formula we can't apply it. Now, so this is mainly for the methods that use memory of the past. Now for SIW, the limitations, I can't see them, to be honest. I can't see direct. I will start first with Transil, the last method. The drawback of this method is that we assume that we have a reference data set on which we allow to have validation memory, and we compute on it the calibration scores before to transfer them. So in cases where it's like, this is a big assumptions, in the sense that if we don't have reference data sets in the same domain of our data set, we won't be able to have these calibration parameters. So this is in the part of Transil. Now for the SIW, I'm sorry, I don't see immediately.
Okay, no, but I think it's fine. I think you covered most of the things that I wanted.
Okay.
Okay, so well, that's for me for now at least. So thank you.
Thank you.
Thanks. I was wondering if it's possible to see the member of the jury. Maybe stop to
share.
To share, yes. Yes, it would be better. I propose to give the speech to David Filia, who is professor at ENSTA Paris.
You cannot hear anything. I don't know if somebody is talking.
Same for me.
I see it's trying to connect to see. It says interference.
Do you hear me here?
Yes.
Okay, sorry. So we tried with a second computer, but it's a complete failure. So I will start again. So I was just starting to talk about the manuscript of Eden. I was saying that it was very nice to have so many explanation of the state of the art, so many different contributions, and so many evaluation of the contribution, in particular on very difficult and large data set compared to a lot of papers in incremental learning, which are often on very smaller and toy data sets. So it was very nice to have all this evaluation. There is a small downside of all this work is that it's quite difficult to follow everything, and you have a lot of acronyms, a lot of new methods, and when you get in the text, when you don't dive directly into a text, it's a bit difficult to follow. But with respect to this, your presentation here was very nice, very complimentary. That's a very clear description of all the method. It was easy to compare them, and you made a very nice description of the results, showing the highlights, which was very nice. So a few questions. One first question is a bit theoretical. So I had one student working on continual learning, and in the end, he was working on the fact that when you use regularization without memory of the past, like we were thinking a lot about elastic weight consolidation, for example. And one of the problems with that is that when you get new data without seeing the old data, you have absolutely no way to compare and classify new data versus old data. So obviously you still have the knowledge of your past data in your weights in your network, and if your new data is a bit different, you will be able to make a difference. But if your new class is quite close to an old class, there is no way to make a difference between that, and it seems to be quite a limitation for him, at least. What do you think about that? Is it a strong limitation, or is it something that we manage to overcome in practical scenarios?
Well, first, when we learn the new class, normally we add a neuron for it in the classification layer. So normally, when we inject the images of the neuron of this class in the neural network, we will activate the outputs of this class. Now, in terms of neuron, normally there should be no confusion. Now, in terms of the representation of the model itself, I think it depends on the difficulty of the data sets. There are data sets when, yes, maybe you can find, for example, it's the case of ImageNet, because there are many types of dogs, and because we use leaf classes, we say this is, I don't know, this kind of dog, and this is the second type of dog, and both of them are dogs. But in our case, I mean, I don't think it's a limitation, because anyway, two different types of dogs, they have two different visual similarities. So for me, it does not really depend on the method, but more on the difficulty of the data set and the similarity between the different classes in the data set.
Yeah, sure. I think it's quite related to the difference between generative models and discriminative models, in fact. So with generative models, you model the probability of each classes. And so if classes are very close, it's difficult to make a difference. Yes. So if you use discrimination between the two classes, you can separate better. And so, yeah, it's clearly completely linked. A few questions about your different contributions, so I will not go through all of them. Just, for example, between the first two among the first, IL2M and scale. So scale is normalizing the classifier instead of just the last probability output. So scale seems to be better in most of the evaluation. Do you think that there is any interest in the previous one, IL2M, compared to scale, or is it just an old method and we should use scale?
the only advantage that I see is that IELTS 1 takes less memory when we save the statistics for it. So it's really dependent on how much we save to be able to rectify this class. So it's simpler and it has less. And also computational time. The computations time is faster IELTS than skill.
Okay, I really liked your trans IL method. So you calibrate the correction parameters for the previous classes. I think the way you are doing it, it's quite related to the number of classes for each task, for example. Is it possible to adapt it, or will it work if you have, so if you train on the reference dataset with 10 classes, 10 classes, 10 classes, and then in your new task you have 5, 5, 7, 3.
Exactly. In these experiments, we assume that all the reference datasets and test target datasets, they have the same number of classes in total, and also in terms of number of classes in each incremental state. So we did not investigate the possibility to have different number of classes, but I think is doable. I mean, it could be an interesting direction of research to see from which calibration parameters I will take, from which subset, or how can I expand it to because if you can see here, the variance between the calibration parameters is not high, so I guess that there will be also always a way to see how we can combine some calibration parameters in order to reduce the number of them, or increase them.
Okay. So that would be an extension. Just in your manuscript, I noted in my report, I think that this method is not compared to the other one in the last section of chapter 4.
Yes.
Am I correct? Is there it's just a technical reason?
Or is because the evaluation in section 4, it was published in a journal paper more than 1 year ago, and this method is the newest one. So we did it only we published it 1 month ago, and for this it was not included in the study. Okay. And also, since the deadline was approaching, we did not have time to try on large-scale datasets. So for this, we use only 100 classes, and the methods in the study, they were more focused on large-scale datasets. So this difference between the datasets didn't make us to put it in the manuscript.
Okay, no problem. It's quite usual to not have time to do everything, particularly given the number of trials you have made. But do you have an idea? Would it outperform the other methods, or?
I guess so, because it's the method that has the largest gains. As I already showed here, on top of Lucille, we gain up to 14 points on this dataset, for example, and is the largest gain that we obtained until now. And the advantage of this method is that we apply it on top of other methods, that not only we use the gain of this method, but also we get a gain that is larger than their gains, because it's applied on top of them.
So in the manuscript, you talked about another contribution about active learning, so choose to not present it here, yes. which is nice. But I was quite interested in that, in particular because I think that the conclusion is mostly that selecting random sample is quite good, and balancing the number of samples for each class is also one of the best methods. Is it correct? Is it or is there?
Yes. In fact, random selection in active learning is until now one of the strongest baselines. So people are trying to have a better performance than a random selection. So it's so difficult in active learning to have a better selection than a random selection. And this is our active learning paper, that our method works, but the performance on top compared to random, it was just a little bit. I mean, we didn't gain too much, and yeah, it was quite difficult to improve more than random selection.
Yeah, it's often the case. So I really liked the idea of associating active learning and continual learning. Maybe one more possibility of future work. You could also take techniques from unsupervised learning and associate it with continual learning. Did you add any thought, any idea in this direction? Is it something that you consider? So the idea of having new without labels, exploiting them.
We had decided this, but we could not go into this direction because we had more ideas supervised learning type, and for this reason, yeah, we just continued the supervised, and we didn't have time to tackle also unsupervised learning. But I think I saw only one paper or maximum two that tackle supervised learning in continual manner, because it's quite difficult. Because even with supervision, you can see the gap with joint training. So in unsupervised learning, I think it will be quite harder to get better results, good results.
Yeah, one of the arguments is that with unsupervised learning, you could have a lot more data, so we could balance the fact that performance are hard. Okay, just two last questions. So in the end of your manuscript, you have a very nice analysis of memory complexity of all your methods. And one of the interesting things, I think, is that it always remains quite low. Highest one is 2 megabytes, which by today's standard is very small. Well, you can always find context where it's a lot, but and given that, you could say that maybe, well, does it worth all the work to reduce the memory requirements so much? And if you add more memory, if you authorize 100 megabytes or 500 megabytes, what would be the best way to use this memory to improve performance?
It's either to save more statistics more than just a mean, that is a single floating point. So, or we can, I don't know, maybe save parts of the neural network in the same time to don't exceed the size of one model that is used in distillation-based methods. So one resonance 18 model takes approximately 85 megas. So if we allow to save parts of the neural networks, for example, the layers that we think they have more information about the past, it could be interesting to save them in memory. And also we can, for example, combine images with feature vectors. So yeah, for me, 80 megabytes of the model is a lot. I mean, more if we work in embedded systems or things like this. So it's something, yeah. So yeah.
Okay, thank you. And one last question, you already discussed that with the previous reviewer. In your conclusion, you mentioned the idea of extending toward domain incremental learning. So the idea of having samples coming and maybe having samples from the past. So you said that it will improve the results, obviously, but do you have any particular possible extension in this direction? Is there something to do, or is just the fact that your model will probably perform better?
No, we did not perform any experiments from this kind. Yeah, from what I said normally our methods are assume that the data appears in groups of classes, and this is how we tackle it all the way in this thesis. However, it could be interesting to investigate also this direction, but yeah, we did not explore it yet.
Okay, thank you very much.
Thank you.
So now the examinators, I propose to let's pick Tine Tutelard from Catholic University in Belgium.
Okay, so first, congratulations with the lots of work that has been done. You haven't proposed just 1 or 2 approaches, but you have like 6 or 7. I don't know. I didn't count, but there's like so many different variations and methods you proposed. So that's nice. And also, as already said, the extensive experiments, like even though it's large scale, a lot of people shy away from that because it takes much longer to run experiments and get stuff done. But it's really nice that in spite of going for the large scale, you still have the extensive evaluations and all the tables and such. So that's really interesting to see how things behave under that setting. So I really liked reading the thesis. Coming to the questions, maybe I would like to ask you first to maybe go to slide number 5.
Yes.
Okay, so this is just one example, but you have a lot of figures like this in your thesis.
Yes.
I really like this way of analyzing the catastrophic forgetting and the behavior of the different methods over time. And it really seems that you use this as your main analysis tool to see, okay, how can we improve, how can we reduce the gap between these red and the blue dots in the figure. And you actually manage, and you see through the thesis that they get closer and closer to each other. And that's what we want to have. And so just presenting the data in this way helps in really seeing, okay, how can we close that gap and how what do we need to get there. So I find this analysis tool by itself actually also a nice contribution or original way of looking at things. One thing that one immediately notice when looking at these plots is that not just the red dots are lower than the blue dots, but also they seem kind of correlated. When you have an easier task, or when for some reason the blue dots go up, also the red dots seem to go up, and vice versa. When the blue dots go down, also the red dots go down. Yes. So do you have an intuition why that is?
My only intuition is that the earlier layers before the classification one, they keep anyway information from the past. And this is what we hypothesize in our methods, that the forgetting mainly appears in the classification layer. And here I will present, sorry, I will go until the end for the backup slide. Because in this experiment here, we try to see the mean feature similarities between the last states and all the states before. So we take the testing image of the first batch of classes. We pass them to all the network in all the incremental states, and after we compute their cosine similarity with the features in the last state. And we can see here that even when we vary the memory size from 2% until no memory of the past, we see that the features similarity does not evolve too much. So we conclude that the earlier layers, they keep information, and the classification layer is the one that suffers more from the forgetting. For this reason, if a class is difficult, that is passed, and in this state, so also it will suffer to learn the new class in the same state.
Yeah, and then, but also the other way around, when you then have later an easier task with classes that are easier to discriminate, you not only improve on the new classes, but you also seem to improve on the old classes.
Yes.
So how do you explain that?
I don't have explanation for this particular case, but let me just come back, please. I don't have a particular explanation for this. Yeah.
Yeah. Okay. So it's just an observation that I thought, like, because you probably have been looking at these plots quite a bit. I wanted to check with you. Moving on, the method that I found most intriguing is scale.
Yes.
Because there you don't only work at the output predictions, but indeed at the weights of the last layer. Now sometimes you use the words weights and sometimes you use the words weights activations. But so am I correct in saying that what you change is the actual weights of your last linear classifier, right?
Yes, is the weights of the class. Yeah.
And then what's weird or what's special there is that you don't use the same, like in the previous method, you only change the output prediction, so it's kind of you change the confidence. But here, different weights in your linear classifier get rescaled differently, which means that if you think of it as a linear classifier in your representation space, you basically change the orientation of your linear classifier, right?
Yes, but for this reason, we propose to do the normalization of the weights in order to rectify them and to don't let the orientation goes from all the directions, since we combine the weights from different states. So for this reason, we propose here the normalization that we computed on the mean vector scores in all the states. And simply in the SIW method, we found that only the standardization could fix this problem of orientations and normalize all the class weights.
Yeah. So here you say basically, it's in the end only the normal distributions that matter. So did you compare directly to what extent SIW has the same effects as scale? So you have less parameters, less degrees of freedom, but how correlated are these two rectifications?
It is true that we did not conduct experiment to see the effect of SIW on the classification scores, and thank you for mentioning it, because I completely forgot about it. We only since the initial experiments was on the weights magnitudes, and it's like in this case I said, well, in this figure, as I see the orange magnitudes are lower, my goal is to make them more comparable. But it is true that I did not check how the scores are after the rectification.
Yeah. Okay. And then I had another question related. Yeah, and then maybe so in the scale, you say you apply this rectification only to the top 10 best scoring old classes, right?
Yes.
And then I don't remember whether in SIW you do that as well, or you do it to all classes there?
In SIW, we do it on all classes, including the new classes, and this what gave us best results.
Yeah, but then why do you need to have this selection of doing it only on, because I thought like doing it only on the top 10 also brings some extra robustness, because you basically have two filters or two classifiers. First, you have the non-rectified one, that needs to give a high score, and then the rectified one has to give a high score. But then SIW, you don't do it that way.
We did it experimentally on when we were doing the preliminary experiments, and only experimentally we found that in SIW it worked better when we normalize all the class scores, because also we tried to normalize only the scores of past classes. We tried to normalize a part of these scores, and experimentally it did not work. So theoretically I don't have explanation for it. But it was this choice was done experimentally on scale and on SIW.
Yeah. Could it be a kind of overfitting that in the because with scale you have more parameters basically that you adapt that in some, yeah, I don't know. Yeah, okay. Then maybe a last question on the like your I guess in slide 50, your conclusions on the methods without a memory.
Yes.
Basically, you conclude diesel actually. I guess previous slide. Basically, diesel seems to work best, and that's kind of frustrating almost in continual learning. We try to come up with all fancy methods, and in the end, just using a fixed representation seems to actually beat them all. And probably if you don't take just a representation learned on the first classes, but you take some of these universal representations learned with really huge amounts of data, like these self-supervised methods and so on, probably it would even work better. And so in practice, then the question is, how far are we with continual learning if just freezing the representations and then doing something simple on top of that works so well? So would you agree, or so what's your view on this?
It's true that for us it was a little bit frustrating, because diesel, we developed this method during my internship, master's internship, and during all the thesis we were trying to beat this result and we couldn't. Diesel, it is true that it is simple method that it gives us the idea to think again about all what is being proposed in the state of the art, and think maybe that simple methods work better than sophisticated losses that we see now in almost on the papers. So it's maybe give us an idea to wait a little bit and check first the easiest baselines. And depending on this, we start to propose more complicated things. So diesel was a little bit surprising in terms of the results, but it is true that the problem with continual learning is that once we start to perform rehearsals on our neural network, it's completely start to forget the data. And fixed representation based, like they assume that the first representation is good, and if we freeze this knowledge and we won't let it forget any information, we can transfer this knowledge to the subsequent classes. And it is true that in these specific experiments, we train the fixed representation on the first batch of classes for comparability, but it does not mean that in practice we will do it. So in practice, yes, we can use universal representations learned on ImageNet or other datasets, and after transfer the knowledge to other domains. However, in some specific applications where we have special data distributions, maybe, and we don't have enough data to train a large fixed representation, maybe in this kind of applications, we won't use diesel and select other methods that start from the first batch of classes and update the neural network depending on what we want to do later.
Yeah, I fully agree. So in diesel, you use support vector machines for your classifiers.
Yes.
So how crucial or how important is that? Because you at that stage you mostly compared with iCarl, and then I guess the difference is mostly indeed using when you do when you use a fixed representation, at least use all the data when you have it available. That's a strong point that you make. But then you also switch from like a mean classifier to SVMs. Is it important to use SVMs, or is it just any classifier would do the job?
It is true that we did not vary the type of the linear classifiers. We only tried SVMs. We tried, the ones that we deploy are one versus rest fashion. And we tried SVMs with multi-classes. They didn't perform better than one versus rest. And the only other classifier that we tried was multi-layer perceptron, but it was harder to optimize. And also it takes more time to train than the SVMs. But it would be interesting to try other linear classifiers. And it's something that we didn't do in this paper.
Yeah. Okay, that's all for me. Thank you.
Thank you.
Thank you, Tim. So next one is Simeon Papadopoulos, senior researcher in thèse IT in Greece. Simeon?
Yes, hello. First of all, again, congratulations. This was really a great PhD, very comprehensive, very coherent, with very clear and good contributions. And I also would like to thank Adrian for inviting me in this committee. It's an honor for me to be in this committee. I have some general remarks, which I'm going to take first. The first one is kind of similar to one that Niku raised. And I'm curious, what is the behavior of the methods you propose when we want to learn some more fine-grained classes of a class that appeared previously? I think Niku's question was more on a concept drift nature, but I'm mostly referring to cases where the general class remains the same, but we want, to learn some finer classes in the new states. How would this affect the learning?
We did not perform such experiments. For us, we just take one data set and we select randomly the classes from it, and we based on it, we consider that its class is different. And it is true that we did not see if there is relationships between the classes inside the data sets. I guess, yes, there are many, at least in ILS-VRC data sets, when we can find, as I already said, for them, different kinds of dogs, different kinds of cats. But for us, we simply consider that each type of dog is different class, even if it's just finer grained class of it, and that's all. I mean, I don't know. We did not perform study on this in this specific property.
Okay.
And it is in general what is done in the state of the art. So there are really few studies that they focus on the content of the data set itself. In general, most of the people, they take one data set, they shuffle the classes, they divide it in different states, and they consider that each class is different from the other, and they learn with it.
Do you think there would be any interest, any merit in trying out to, especially into your methods that use some kind of statistics about classes, to try to take into account correlations among classes?
Yes, of course, it will be interesting to check the similarities between the classes that we are learning and use for example, there are methods that free some parameters in the neural network in order to accommodate the new knowledge. So if we suppose that these specific parameters are good for this class, but in the same way, this class has a large similarity with another class, we can just keep them in the same group of parameters in the neural network. And like this, we free more space in the neural network. So this similarity between the classes make us share information between them to learn them more effectively.
Okay, then I would like to challenge a bit your one of your main motivations. I think this goes a bit also in the direction of one of David's comments. It seems that you are mainly driven by the fact that in some applications we are not allowed to use memory or use very limited memory. Actually, if we don't consider applications like embedded systems that you mentioned before, I find it hard to see which other application contexts this kind of constraints appear. You mentioned also medical data on grounds of privacy, but I think that even then we would be able, to use either kinds of encryption or use only feature vectors, which typically they are not considered as privacy intrusive. So I wonder whether this really is such a big constraint in practice, or you have some very specific applications in mind.
It could be also the security applications. For example, if we suppose that we will develop a system for the government and there are some secret data that was trained in the past, and they just want to include the new data in their system without to have access to the past data. So it's not only constrained to the medical domain, but to all the domains where we are not allowed to keep the data. We can see also this in edge computing, where there are systems that learn how can I say real time. They learn real time, and they don't have the right to store the data for privacy issues. For example, if it's a camera and the system that we are developing, it handles people, and these people, they don't want that we keep their images. Assume that this camera is in the street, for example, so we don't keep images for these people. So we with edge computing, we update our system continually from the data of these people that pass, but we don't have at all the right to keep their data in the system. So whenever the image arrives, it passes to the neural network, and that's all. We don't keep it. And in these applications, it's important to don't have at all a memory, not even for the new classes. So even the new classes, they don't have. We shouldn't keep them in the memory. So the image passed to the camera, and we learn it, and that's all. So it's more edge computing applications or security applications.
Let me put then the question in a kind of different form. One of your main conclusions, and it's quite obvious from the experimental results, is that there is still a very big gap compared to joint learning. So when you really have everything available. That in several applications, this kind of gap, so this higher error rate, translates into some important KPIs like losing profits, making wrong decisions, even affecting people's lives. In such cases, do you think it is really, would you recommend to deploy such methods with this risk of making errors at a such higher rate, or would you try to, and somehow find ways to circumvent these memory-less constraints?
It depends on the sensitivity of the task that we are trying to learn. If it's really risky, and I would say for an autonomous car or something like this, I do not recommend to use incremental learning methods without memory, of course, until the enough performance is obtained. And for this reason, the researchers are working on it in over the world. Now, in applications that are not sensitive, it would be okay to use incremental learning because it will help us to gain the memory, the time, and the computational resources. So it really depends on the sensitivity of what we want to do.
Okay. And one other question relates to the use of knowledge distillation. It seems that based on your work, it is an approach that is not effective, especially in large scale. Do you think that there are any, ways to circumvent that, or it's a kind of a lost battle? And one more particular question related to this is, do you think that if we could keep more teacher models that are perhaps each teacher model focuses on each state and we could use all of them together, do you think that this could work?
There is already one work about this in the literature where they use one teacher model per task to distill the knowledge. The thing is that in this thesis, we focus on methods that they don't increase the architecture of the neural network. For this reason, we did not explore this direction because we assume that we only have one model and we have to use it to learn the data. But of course, the more resources we have, the more models we can keep. And here we can find the application of task incremental learning methods that in general, they use one model per task with one gating mechanism to select which model to use for inference. And yeah, it is possible, but regarding the complexity of the neural network that is increasing, the more we have tasks, we don't use this type of methods because our goal is to be able to learn infinitely. So if we have increase in number of models at large scale, it will be costly.
I see. And then I have some questions, more like clarifications that it's probably my fault that I didn't really understand by reading the manuscript. I don't know if it makes sense to raise them here, or I could just send them. What is the process?
If you would like a relaxed discussion about it, you can send them later. If you want short answers, I can answer them now.
Okay, let's try then briefly. But if you think that it would need a lot of time, then don't worry about it a lot. The first piece of text that I found a bit hard to grasp is in page 30 of your manuscript in section 2.2.1.
I don't have the manuscript.
You don't? Oh, then maybe it does.
It's not my machine, and
okay, then maybe it doesn't make sense to do this now. Then I will just ask you two things that are easy without reference to the manuscript.
Okay.
Or actually three, because one also is in your slides. So the one question is, when you presented the background, the related work in section 2, you made a reference to a comparative study which inspired your classification of the existing methods. I was wondering, is this the only kind of survey-like paper in the area, or are there more?
There are more and more now. In the beginning of this thesis, there was only one, I think, or maximum two. Now there are 4 or 5 studies. And the most recent one is done by Masana and his colleagues in 2021. And in this study, he focused on class incremental learning methods, and it's really interesting survey because they vary lots of parameters more than we did in our survey, and they vary the neural network architectures, and they really do a more complete study than us.
Okay, okay. So it seems that it's really a kind of highly evolving and hot area. Then in DSIL, you choose to use 20,000 negative samples, so 20 images per class. Is this a kind of rule of thumb that you recommend in every case, or did you try out different options?
I didn't understand the question. Can you repeat, please?
In DSIL, you used 20,000 negative samples in your setup. So I'm wondering whether this 20 images per class is something that is, you know, kind of intuitive or rule of thumb, or is, or you tried out also different options?
In the time we published DSIL, the most popular method, it was iCarl, and based on this we proposed DSIL to tackle the problem. And in iCarl, it's them who used 10 states in ImageNet and CIFAR, and a memory size of 20,000. So when we proposed DSIL, we used the same parameters and 10 states and 20,000. However, in the journal paper and in the experiments that they showed today in the defense, we tried DSIL with different number of states between 10, 20, and 50, and also we vary the memory size between 20,000, 10,000, 5,000, and no memory of the past.
Okay, right. Okay, and the question is about figure 4.3, which I think appears also in slide 11.
Okay.
Your slides. Or not? No, it was 11. I was looking at what is down. It was 11/13 or something. Now. It was where you present the similarities between features.
Okay, it's in the backup slides.
Okay,
Yeah.
Didn't notice. That one, yes. First of all, here, just by inspection, I'm not sure if there is any significant difference between the 1% and 2% of memory. Is there any important difference, or is it almost the same?
The main difference is here between the state number 7 and 8. Here in the memory 1, it increases. So we really have to focus very well here. Also, we can see that this curve here is different from that one. But the main idea of this figure is to show that even when we vary the memory size from 2% until no memory, at all the features are still comparable. And that's why we tackle more forgetting in the classification layer.
Sorry if I missed this, because you probably also explained it before, but is this kind of abrupt change towards the end something expected?
It was not expected because we thought that catastrophic appears in all the layers of the neural networks in the same way until we did the experiments about the mean prediction scores between past and new classes, and we found that the gap is large. So we proposed the first methods, IL2M and scale, that work on this specific layer. And because we obtained large gains only on working on the classification layer, we said, let's see how these features are evolving through the incremental states. And we found that the feature similarities, it does not evolve too much. And it is also an explanation for why the working on the classification layer gains lots of accuracy.
Right, right. Okay, thank you very much again. Really congratulations. And yes, this was really a very, very interesting and comprehensive work.
Thank you.
Thank you. I propose now to give the speak to your supervisor. So, Adrian, maybe, or Johannes? You begin?
I have no questions.
You have no questions, but maybe...
3.5 years to ask questions.
Go on, Andrea, if you wish.
I was saying that I have no questions since we had 3.5 years, so I had 3.5 years to ask them. What I want to say is that I really enjoyed working with you, and I want to congratulate you for the results. And I thank you for all the hard work and for being available throughout the whole period, especially given the special circumstances that we all live in. But yeah, that's life. So thanks a lot, and again, congratulations.
Thank you very much. Thanks to you.
Johannes?
Thank you, Celine. As far as Adrian has no question to do, generally he has questions. I have the duty to do it in order to replace him. And I propose you to give some elements that could be interested for a general public, but also for the first time, because generally I'm not asking questions of the work of a PhD student. For the first time, I'm going to do it, if you allow me. And then perhaps because it is presumably the last PhD of my career, in at least at such questions that started, if my memory is not quite destroyed. It's a question of forgetting, catastrophic memory, you see. The first who started these questions was Adrian himself, at about 13 years before your PhD, Eden. If one has in mind the works of Adrian and then other PhD students who got together, one could see or identify common characteristics of these works. The main, that is also a mystery for me, I'm going to explain why, is something that I could call it an engineering, I know I don't find the correct word, perhaps resourcefulness. It's the genius aspect of engineering, and its expression, to my opinion, is that rather simple operations, I'm going to come back to this question, lead to very efficient results. I tried many times to destroy, to enter this mystery without be very convinced of my investigation. But I'll give you some examples in the form of a question, just to illustrate it. For instance, page 21, slide 21, Eden. We can also, 21. I could also say the same thing to 27 or 26 many times. We have the formula 5, an equation, and we remark that with such a mathematical tool, we have very good score rectifications with the rectification. Why not to affect it by some factor? I mean, for instance, multiplying 2 or 3. We got many times the opportunity to have fun together, and then it was many times laughing with questions like that. And at the end, you were very well anticipating them. But for instance, here, we are in front of a mathematical formula that could be alterated by factors, and perhaps these factors could give better and better performances. What is the mystery between such mathematical operations and the good scores of rectification given by the rectification, to your opinion?
There is no mystery. Our ideas are.
Can you please speak more louder? I mean, because
Okay,
we
I
have
said
some
that-
difficulty to hear you.
I said there is no mystery behind the formulas. It's just that we follow our intuitions without to complicate the formula. In this specific case, we come back to this graphic. I said when we learn the class for the first time with all its data, it means it's a new class, so it has a large prediction score, as we saw in the graphics of the mean prediction scores. Now, when I move to the subsequent states, the past classes, it means the class 1 or 2 that they were new in this state, now they have scores that are degradation in this state, so they are low. And so the basic idea behind this formula is that if I take the score of the past class that is bad in this state, I will multiply it by the score in the initial state that is high, it's higher, and I divide it by the mean score in the current state that is a low value. So here, if I divide a big value on a small value, it will automatically increase the score of the class. It means if on average the score of the class in this state is 4 times, for example, greater than the original score of the class, so I will multiply it by 4. It's true that we did not take into account the variance between the scores of the past classes. That's why we have this figure. It means that the formula is not the best. But in this specific case of IL2M, we did not make this analysis on time. This figure, I make it like 20 days ago. And because the idea when we published IL2M was not really to balance this gap between to reduce this gap between past and class scores and make them more comparable. The idea was more to show that distillation was not working at large scale when we have memory of the past, but to make past this idea, we need to make a contribution of a simple method that will improve the results compared to distillation. So the idea that we noticed the gap, we found this basic formula to increase the scores of past classes, but it is true that we did not see in the moment how much we are increasing these scores. And I discovered this so late in the thesis that IL2M increases the scores of past classes, but not enough to eliminate the gap with new classes. So intuitively, it would be interesting to complicate a little bit more the formula in order to reduce more this gap.
But not complicated. Just add some little factor, coefficient that could reduce, to my opinion, more this gap between past and new classes. Okay. I'm quite sure that this additive value of mystery would give us more questions to understand the correlation between mathematical formulas and the reality. A second question, if you allow me, is the slide 23. Can you, for instance, explain to a larger public why second statement, forgetting, happens mainly in the final layer? Why in the final layer? Or the problem is the final, are the problems are concentrated to the final layer finally?
Just intuitively, the final layer is there where we compute the gradients and start the back propagation, and it's the classification layer. So of course the forgetting more occurs in this layer for the experiment that I already showed in the backup slide when we did the plots of the mean feature similarity between the classes in the initial state and those of the past of the last state, and we found that the features does not evolve a lot when we modify the size of the memory. For this reason, we focus on the classification layer, and in terms of performance, we can see it simply by looking at performance of vanilla fine-tuning. Here we have vanilla fine-tuning with catastrophic forgetting. So here in the first line. So if I just use the initial weights of past classes from their states in which they were learned for the first time, look how much gain in performance. For example, here in VGG face, the accuracy goes until 90%, which is huge. And knowing that in this baseline we don't touch at all the previous layers, we just bring the classification weights of the past classes from their initial states and we override them in the current state. We don't do any normalization, any extra rectification, and we can see how much gain we can obtain just by rectifying this layer. Now, if we want to refine more our method, we have a standardization of initial weights that is simply FT plus init, and we apply on top of it the standardization to normalize the class weights, and we obtain more gain. So this is why I said that the forgetting mainly happen in the classification layer.
Well, you're to the 49 slide. Can you pass to the 42, please? And this is a question that would perhaps be of more interest for at least one of the persons that are present in your presentation. It's another PhD student of me, who works with other types of architecture. The question is why the use of the ResNet 18 network has been chosen. Well, of course, I know the answer, but it would be very interesting to explain. The complementary question is, do you think that changing the architecture, you could have different performances, and in which sense? Which sense you could alter these results you have?
Okay, for the choice
maintaining
of
the same methodology, of course.
Yeah. For the choice of the neural network, it's not us who choose. We just follow the state of the art that all people use ResNet 18 neural network. And for our specific case, as I said, we followed the paper ICAR. It was our starting point for the experimental part. So they used the ResNet 18. We used a ResNet 18 because the goal was to fix how can I say, the configuration of our neural network. And we tried to see which algorithm is working without to modify the neural network. And all people now adopt this neural network. Now, if we change the architecture of the neural network, in this thesis, we did not vary the neural network, but this was done in the study of Masana and his colleagues. So they tried many architectures: mobile nets, Google nets, ResNet 18 that we use in our experiments, AlexNets, and VGG 11. And the surprising results was that sometimes the performance of the algorithms sometimes changes completely. For example, here BIC, the bias correction layer, performs better on mobile net. However, if we test it on VGG net, it has the worst performance. So this was kind of surprising, and this is also they note this also for ICAR, for example. However, also they tried to experiment with our method IL2M, and they found that our IL2M method is the more stable compared to the other methods, and because it does not perform in any case the worst or the best. It's not so extremist than big, that it's passed from the first position to the last position. And in their work, they found that neural networks that they have skip connections, like ResNet 18, in this kind of neural networks, the bias correction method works better. However, in neural networks where there is no skip connections, like AlexNet, the big method does not work. So yeah, this was a surprising result from the state of the art that us in this thesis we did not tackle. But yeah, in this paper it was done, and it could be the performance could change from one architecture to another.
I could refine this question, but I prefer to go forward. Slide 12. You give 6 challenges. You call them challenges, or exigencies, in other words. The question also has something to do with the question of Nico and somehow of Tine. Do you think that one could define for these exigencies some theoretical limits? I mean, we cannot have more than this performance, this accuracy, for instance, or this scalability, for instance, or this complexity, for instance, with this particular architecture.
Okay, I will try to go through them one by one. For the complexity, in my opinion, the layer that should evolve is the classification layer, because we should add the neurons to be able to classify the new classes. So in terms of complexity, in my opinion, we cannot go down below this, the increase of the classification layer. And here I am not speaking about the methods that they compress the neural network. So this is another case that I don't include here. I just suppose that I have ResNet 18 as it is. I will not compress it. I will just let the neural network evolve in the classification layer. In terms of memory, I would say that the limit is to don't use memory at all. I don't find the more difficult scenario than to don't have simply to don't have memory. For the accuracy, I think that the goal of all the method is to approach the accuracy of joint training, in which we have all the data. So I don't know if in the future there will be incremental learning that will be able to outperform a joint training. I don't think so, but I will keep it open. For the timeliness, I don't think there is a minimum delay to be able to include the new data. But for example, in Diesel and also in Remind and Deep SLDA, it takes less than 1 minute to add a new class. So there, I don't find a minimum delay to add the new data. For me, 1 minute is already more than enough because we can train these methods in CPU instead of GPU. For the plasticity stability compromise, I think this depends more on the application domain. If we want the model to keep more knowledge from the past or to adapt more to the new data. So yeah, this I don't find the specific percentage between the plasticity and the stability. And for the scalability, normally an incremental learning should learn an infinite number of classes. Normally we don't have a maximum number of classes that we learn.
And as the application domain is concerned, do you think that we can apply all these methodologies to more than the application domains and tasks you gave us in the beginning of this presentation? For instance, the NLP, natural language processing, could be possible, for instance, to imagine that some of these ideas could be applied for dealing with the language problems?
Yes, of course. There are works who work on the text classification continually, for example. In this thesis, we only focus on image classification, but there are people who do text classification, and there are people who apply also on detection and other tasks. So in classification, I guess that it will be possible to apply these methods. In terms of performance, I can't tell you which method will perform better or not, but yes, it's applicable.
Okay, thank you. Of course, the discussion may continue, but I would like to finish with some, if it is possible, emotional comments. I would like to express and to address also my gratitude to Adrian, who was my PhD student several years before and became very soon my own professor. And I found that all this work with Eden, when you have Adrian and Eden, I think your work is very easy, very, very easy. And I'm very happy to arrive to the end of my academic career with such a quality of a PhD thesis. Thank you, Eden. Thank you, Adrian.
Thank you, Anis. So a lot of questions have been asked, but I have still a few ones.
My first question is very close of one question of Simeon, and it is about the relations between the different class, between the different states you have. And if we take your approach Diesel, do you think that you have some kind of implicit constraint between your classes that exist in your approach?
The implicit constraint is the relationship that exists between the classes learned in the fixed representation and the classes that we learn incrementally. So these have great results, but knowing that all of these classes, initial or not, they have the same distribution. So this is the implicit assumption that we make. Now, if I change the domains between the fixed representations and the classes learned incrementally, the performance of Diesel will decrease. Yes.
And if now you make the hypothesis that you have a domain shift, but you have some information about this domain shift, either statistical or but you have some information. Can you use this information in order to adapt your approach, in order to be robust to this kind of domain shift into this approach?
In this case, maybe I would suggest to combine fixed representation with a model that evolves implicitly, even if it's of a small size, and find a way to combine both of the information together.
Okay, I have some questions regarding the scale interactive learning approach. Do you think that your observation and your conclusion, for instance, in the fact that catastrophic forgetting impact a lot the classification layer, is the same if you have, for instance, a relation from course to find classes in your incremental learning scheme, whereas the contrary, so whereas you have find to course classes.
I think
So according to the relations you can assume between your different classes, do you think that your observation still stays the same?
yes, I think the forgetting will happen anyway, even if we pass from course to find or the inverse. The problem comes from the fact that we update the model weights, even if it's with data of the same class, but we completely don't use the same data of this class for the other data. It will forget the other data. This is the problem, that the neural network adapts its weights depending on what we inject in this moment. Yeah.
Okay. And do you try to apply some explainability tools to your approach, just in order to have a way to inspect the different feature learned during your learning scheme?
No, we did not apply explainable artificial intelligence, but in fact, it could be interesting to see the heat maps,
yes,
and see which parts activate the decision of the neural network. So it's a direction of work that we did not explore in the thesis.
Okay. Okay, and maybe your last questions. I think that I don't remember who, maybe David, related to mixing this kind of learning with other skills, and in particular semi-supervised learning or unsupervised learning. Have you some idea for that? Have you?
No, we did not explore it, but we can, I have maybe a little ideas in the semi-supervised learning, since we already worked on the active learning part. So we have an expert that annotates a budget from the new data. And the idea is to find similarities between these annotated data and the non-annotated data, to associate labels to the non-annotated part and use it for training. So this can be easily tried direction. For the unsupervised part, I don't have idea.
You don't have idea?
Yeah.
Okay. But you do a lot of things. So. Okay. I have any more questions. Maybe if someone in the room has got a PhD, yes? You don't have a PhD. Sorry. So you can. You need a PhD to be allowed to ask some questions. Sorry for that. Yes, and maybe in the remote audience, if a person who has a PhD want to ask a questions, it's now. Okay. If there's no questions, I think that we have to quit the room in order. No.
Well, we shall try. Just stay like there you are, Eden, and the audience, and we shall try to go to another room, virtual room. I hope it will work.
We hope so.